This video is brought to you by mywayteaching.com.
Now let us study another important part of the concept, that is energy stored in a capacitor. So we know a capacitor is a system of two conductors with charge Q and minus Q separated by a dielectric medium, we can say. In order to determine the energy stored in this configuration, consider initially two uncharged conductors 1 and 2. Okay. So initially consider two uncharged conductors 1 and 2 and imagine next a process of transferring charge from conductor 2 to conductor 1. Okay. Bit by bit, so that at the end conductor 1 gets charge Q. By charge conservation, conductor 2 has charge minus Q at the end, as you can see in these figures. So in transferring positive charge from conductor 2 to conductor 1, work will be done externally, isn't it? Since at any stage conductor 1 is at higher potential than conductor 2. So in order to calculate the total work done, we first calculate the work done in a small step involving transfer of an infinitely small amount of charge. So let us consider the intermediate situation when the conductors 1 and 2 have charges Q dash and minus Q dash, intermediate situation. At that stage, the potential difference will be V dash between the conductors 1 and Q. So that will be equal to Q dash by C. So where C is the capacitance of the system. Then imagine that a small charge, that is delta Q dash, is transferred from conductor 2 to conductor 1. So work done in this step is given by delta W dash, resulting in charge Q dash on conductor 1 increasing to Q dash plus delta Q dash. So in that case, this work done is given by delta W is equal to V dash delta Q dash is equal to Q dash by C delta Q dash. Okay. Since delta Q dash can be made as small as we like, we can, this equation, we can write it as delta W is equal to 1 by 2C Q dash plus delta Q dash square minus Q dash square. So here this equation and the one that we studied before, that is delta W is equal to V dash delta Q dash is equal to Q dash by C into delta Q dash, are identical because the term of second order is in delta Q dash. And delta Q dash square by 2C is negligible since delta Q dash is arbitrarily small. So the total work done is the sum of the work over a very large number of steps involved in building the charge Q dash from 0 to Q. So we can write that total work done as sigma sum over all steps Okay, and we can write it as okay. So we can expand this equation. W is equal to 1 by 2C If we expand that equation, that expansion will be like this, and then it will be simplified as q square by 2c. Okay. So the same result can be obtained directly by integration. If you integrate the equation, that is W is equal to 0 to Q dash by C delta Q dash, that is equal to 1 by C Q dash square by 2 limits 0 to Q. We get the same result, that is Q square by 2C. This is not surprising since integration is nothing but summation of large number of small terms, isn't it? So we can write this result, that is q square by 2c, as in other ways, that is 1 by 2 cv square or 1 by 2 qv. Since electrostatic force is conservative, this work is stored in the form of potential energy of the system. For the same reason, the final result for potential energy is independent of the manner in which charge configuration of the capacitor is built up. See, when capacitor discharges, this stored up energy is released. So it is possible to view the potential energy of the capacitor as stored in the electric field between the plates. So in order to see this, for simplicity, consider a parallel plate capacitor and separation D between the plates. In this case, energy stored is given by, for parallel plate capacitor, that is 1 by 2 Q square into C, and area is A. Separation, as I told you, it is D. So the surface charge density sigma is related to electric field by the equation sigma is equal to E is equal to sigma by epsilon. So for parallel plate capacitor, the energy stored is given by 1 by 2 epsilon naught E square into AD. So AD is the volume of the region between the plates. So if we define energy density as energy stored per unit volume of space, this equation shows that energy density of electric field is given by 1 by 2 epsilon naught E square. So now let us see one more simple problem. A 900 picofarad capacitor is charged by a 100-volt battery. How much electrostatic energy is stored by the capacitor? The capacitor is disconnected from the battery and connected to 900 picofarad capacitor. What is the electrostatic energy stored by the system? So these are the two cases. Let us consider for the first case, that is A. So where capacitor is connected to a battery. So the charge on the capacitor, we know it is given by C into V, and C is 900 picofarad, that is 10 raised to minus 12, and V is 100 volts, which is 9 into 10 raised to minus 8 coulomb. The energy stored by the capacitor, we know the formula, that is given by 1 by 2 CV square. So here we know the values, 1 by 2 CV square, and here we don't know the value of we can use this equation also. We know C, we know V. If you want another equation, we can use that also, 1 by 2 into Q into V. So here just now we calculated Q and we know V. So this gives the energy as 4.5 into 10 raised to minus 6 joules. So this is the first part. Coming to the second part, in the steady situation, the two capacitors have their positive plates at the same potential and their negative plates at the same potential. So let the common potential difference be V dash. The charge on each capacitor is Q dash is equal to CV dash. So here they have removed battery and they have connected to another capacitor. So by charge conservation, this Q dash, since it is divided between the two, is equal to Q by 2. So this implies V dash is equal to V by 2. So the total energy of the system will be equal to 2 into 1 by 2 Q dash into V dash, that is 1 by 4 QV, which gives, we know Q, we know V, 2.25 into 10 raised to minus 6 joules. So in going from A to B, though no charge is lost, the final energy is only half the initial energy, whereas the remaining energy gone. Then there is a transient period between the system settles to the situation B. So during that transient period, a transient current flows from the first capacitor to the second, and in that process energy is lost in the form of heat and electromagnetic radiation. So only there is a loss. Coming to the last topic, one-way GRAAFF generator. What is this? Basically, this is a machine that can build up high voltages of the order of few million volts, and the resulting large electric fields are used to accelerate charged particles like electrons, protons, ions to high energies needed for experiments to probe the small scale structure of matter. Okay. And the principle which is used for this machine, suppose we have a large spherical conducting shell of radius r, as you can see here, on which we place a charge q, and this charge spreads itself uniformly all over the sphere, and the field outside the sphere is just that of a point charge q at the center, while the field inside the sphere vanishes. So the potential outside is that of a point charge and inside it is constant. So the value at radius r. So potential inside conducting spherical shell of radius r carrying a charge q is constant, and that potential is given by q by 4 pi epsilon naught into r, isn't it? Now, as you can see in this figure, let us suppose in some way we introduce a small sphere of radius r, as you can see here inside, carrying some charge q into the large one, and we place it at the center. In that case, the potential due to this new charge, it has the following values at the radii indicated. That is, potential due to small sphere of radius r carrying a charge q will be equal to q by 4 pi epsilon into r, and q by 4 pi epsilon naught q by r. This is at surface of small sphere, and this is at surface of large shell. So taking both charges q and q into account, we have for the total potential V and the potential difference values, we should consider both. So that potential difference is given by V of r is equal to 1 by 4 pi epsilon naught q by r plus q by r. And V of r is equal to 1 by 4 pi epsilon naught q by r plus q by r. And the potential difference is given by q by 4 pi epsilon naught 1 by r by 1 by capital R. So now let us assume q is positive. This q is positive. So we see that independent of the amount of charge q that may have accumulated on the larger sphere, and even if it is positive, the inner sphere is always at a higher potential. So the difference V of r minus Vr is positive. So the potential due to q is constant up to radius r, and so cancels out in the difference. Which means if we now connect the smaller and larger sphere by a wire, the charge q on the former will immediately float onto the matter, even though the charge q may be quite large. The natural tendency is for positive charge to move from higher to lower potential, thus provided we are somehow able to introduce the small charged sphere into the larger one. So we can in this way keep filling up larger and large amount of charge on the latter. So this is the principle. It is a machine capable of building potential difference of few million volts, and the fields which are close to the breakdown field of air, that is equal to 3 into 10 raised to 6 volt per meter. A schematic diagram of this Van de Graaff generator you can see here in this figure. A large spherical conducting shell is supported at a height several meters above the ground on an insulating column. A long, narrow, endless belt insulating material like a rubber or silk is wound around the two pulleys. Insulating belt one at ground level, one at the center of the shell, and this bed is kept continuously moving by a motor driving the lower pulley. It continuously carries positive charge sprayed onto it by a brush at ground level to the top, and there it transfers its positive charge to another conducting brush connected to the large shell. Thus, positive charge is transferred to the shell where it spreads out uniformly on the outer surface. In this way, voltage differences of as much as 6 or 8 million volts can be built up using this Van de Graaff generator. You can see this is a schematic diagram.